Hello, and welcome to this presentation on the bisection method. This is a numerical technique used to solve implicit equations. An overview of the solution of equations. In exercise 1, we're asked to solve the following three equations. In part 1, we're given a quadratic equation 3x squared minus 10x is equal to 14. To solve this, we simply rearrange the equation to have all the terms onto one side of the equation, and then we use a quadratic formula to find the two values of x given here on the right hand side. In part 2, we have an equation involving an exponential function, 2 multiplied by e to the x is equal to 72. We simply rearrange the equation to get e to the x on its own on the left hand side, and then take natural logs, ln functions, of both sides of the equation to find the solution given. And part 3, we've got a trigonometric equation, cos of theta is equal to half. We simply take the cos to the minus 1 or arc cos of both sides of the equation to find the values of theta. Don't forget, when we solve this equation between 0 and 360 degrees or 0 and 2 pi radians, there will be two solutions, and both solutions are given in the brackets in both radians and degrees. I would encourage you to stop the presentation here and solve these three equations using standard techniques. Solutions are shown on the following slide. Exercise 1, part 1 solution. We were given the quadratic equation 3x squared minus 10x equal to 14. We simply rearrange the equation so it equates to 0, have all the terms on one side. In other words, we're going to take 14 from both sides of the equation. That's now the form y is equal to ax squared plus bx plus c, where in this case y is equal to 0, a is equal to 3, b is equal to negative 10, and c is equal to negative 14. We're going to use a quadratic formula to solve for the two values of x. So x is equal to negative b plus or minus square root of b squared minus 4ac, all divided by 2a. Inserting the values for a, b and c, we find two values of x. X is 4.395, which would be this root up here, and also x is equal to negative 1.062, which would be the second root shown here. Exercise 1, part 2 solution. We're given the equation 2 multiplied by e to the x equal to 72. To solve this, we simply rearrange the equation for e to the x. So divide both sides by 2, we get e to the x equal to 36, and then take the ln functions, natural log functions of both sides of the equation, and x is equal to the ln of 36, which is 3.584. Exercise 1, part 3 solution. We're given the equation cos theta is equal to a half. To solve this equation for theta, we simply take cos to the minus 1 functions of both sides of the equation, so inverse cos functions. So theta becomes cos to the minus 1 of 0.5, or half in this case, and don't forget between 0 and 360 degrees there will be two solutions, 60 degrees and also 300 degrees. Solution of equations continued. What we note from the previous slides is that all these solutions were a direct solution, either rearranging the equation and then using a standard formula, or transposing the equation and taking inverse functions. These are termed explicit equations, and they can be solved directly by rearranging the equation or using the appropriate formula, as was shown on the previous solutions. However, in the following equations shown below, these cannot be arranged and solved directly. For example, y is equal to x cubed divided by 3 minus x squared divided by 2 minus 6x plus 5 divided by 3 cannot be solved by rearranging or by use of any standard formula. Similarly, x plus 3 is equal to e to the x. Again, that cannot be solved directly. These are termed implicit equations and must be solved using what are called numerical methods, and the bisection method is such a numerical method for solving this type of equation, as will be shown on the following slides. The bisection method. By using functional notation, it is possible to determine the vicinity of a root of an equation by the occurrence of a change of sign. That is, if x1 and x2 are such that the function of x1 and the function of x2 have opposing signs, then there is at least one root of the equation, function of x, that equals to 0 in the interval between the x1 and the x2. This is provided that the function of x is a continuous function, and they will be in this presentation. So in the bisection method, the midpoint of the interval, we call that x3, which is a half of x1 plus x2, is calculated. And from the sign of the function of x3, it can be deduced whether the root now lies in the half interval to the left or the right of the x3 value. Whichever half interval is indicated from our calculation, then the midpoint of this interval is now calculated and the procedure repeated. The bisection method continued. One problem with this method is that it often requires many iterations and therefore can be quite slow, although it will eventually always produce the root. The procedure stops when the two successive values of x are equal to the required degree of accuracy. The increasing degree of accuracy increases the number of iterations required. Examples of the bisection method iterative solution process are now shown on the following slide. Example 1. So we're going to solve the equation y is equal to 3x squared minus 10x equal to 14, solved previously using the quadratic formula. Using the bisection method, we're going to find the positive root first of all to two significant figures. So in the solution for the bisection method, we have to endeavour to determine an approximate location for, in this case, the positive root of the equation by sketching or by trial and error, whichever technique you prefer. So using functional notation, that's the fx notation on the left hand side here, that's equal to, in this case, 3x squared minus 10x minus 14. All I've done there is rearrange the equation to get all the terms on one side, and it equals to the function of x, or the y dimension. So if we now sketch the function of x here, the y is equal to 3x squared minus 10x minus 14, we would get this shape of quadratic. We can see from the plot of the equation that the positive root resides between 4 and 4.5 on our x-axis. That's a root because that's where the y value, the function of x, is 0. So that would give us our first estimate between 4 and 4.5. An alternative method is used the trial and error approach. Here we've got our function of x in this column, that's a 3x squared minus 10x minus 14, and here is the remainder, the y value, the function of x value, when we put the x value into the equation. So for example, if you put 6 into the equation for x, we will get 3 multiplied by 6 squared minus 10 multiplied by 6 minus 14, and that gives a value of 34. If we now put the value of 5 into the equation for function of x, we get 3 multiplied by 5 squared minus 10 multiplied by 5 minus 14, and that gives a value of 11. If we now put 4 into the equation, so the function of x is equal to 3 multiplied by 4 squared minus 10 times 4 minus 14, we now get a negative 6 value. So we've got a change of sign here. So we know that a root must occur between the x is equal to 4 and the x is equal to 5 values. So again, that's our starting point for the bisection method. If we continue putting values into the equation and put 3, 2, 1, 0, negative 1 and negative 2, we can see another root occurs because of the sign change between negative 1 and negative 2 on the x-axis. So if we're looking for the negative root, then we can use the limits of negative 1 and negative 2 in our solution for the bisection method. We'll look at that later on. So unfortunately with these numerical methods, you must have some indication of where the solution is before you can start the bisection process in numerical method solution. So by either sketching the graph or, as I said, using the trial and error approach, we can home in hopefully on the location, the vicinity of the roots. Example 1 continue. So part 1, we're trying to find the positive root first of all. So from our table on the previous slide, or our sketch of the curve, we find a root occurs between x is equal to 4 and x is equal to 5. So we're going to try a value of x of 4 plus 5 divided by 2, we're averaging in other words. So our first value of x we're going to use is 4.5. So using our functional notation, that's now written as function of 4.5, that's the x value, and all I do now is put 4.5 into the equation on the previous slide, so that's 3 multiplied by the x squared, so that's 3 multiplied by 4.5 squared, minus 10 multiplied by the x is 4.5, minus the 14. That gives a value of 1.75 as a remainder. Now noting that x is equal to 4 has a negative remainder, we find that on the previous slide for the value of 4 here, we have a negative 6, or negative remainder. And now we found that x is equal to 4.5 has a positive remainder, then there must be a root between x is equal to 4 and x is equal to 4.5. So straight away we start to focus in on our root. So my x1 value for my first iteration will be 4, what's called the lower limit, and my x2 value will be 4.5, and that's the upper limit. In this process I find the x3 value, which is simply the average of the x1 plus x2, so a half of x1 plus x2. So in this case that's a half of 4 plus 4.5, that gives me a value of 4.25. I now put the value of 4.25, the x3, into the functional notation equation. So now I get 3 multiplied by the x3, 4.25 squared, minus 10 multiplied by the x3 value of 4.25, minus 14. That gives me a value of negative 2.313. Now, as the remainder at x is equal to 4 and x is equal to 4.25 are both negative, no root can occur between that interval. So the root that we're looking for must occur between the x is equal to 4.25 and the x is equal to 4.5 range. So what we're going to do now is increase the lower limit but keep the upper limit as we go for the interval on the right hand side of the 4.25 x3 value. So now for our second iteration we now have 4.25 as a lower limit and 4.5 as the upper limit. We know a root must occur there because the remainder for 4.25 from above is a negative 2.313 and the remainder for the 4.5 shown up here is positive 1.75. So a root must occur between those two increments. All we do now is repeat the entire process as we did for iteration 1. So now we find the value of x3, which is a half of the x1 plus the x2 in this case, so 4.25 plus the 4.5. That gives a value of 4.375. We then put the value of x3 into our equation, our functional notation here. So put in 4.375 into the equation above. Working it out, we get a negative 0.328. Now as there's no change in the sign at x is equal to 4.375, it's still negative in this particular case. The root must occur between 4.375 and 4.5. Because we know at 4.25 we have a negative root, we now know at 4.375 we have a negative root, so the interval we're looking for now will be 4.375 to 4.5. So that's going to form our third iteration. X is equal to 4.375 and x is equal to 4.5. So we've increased the lower limit again, but we've kept the upper limit. So for our third iteration, we're looking at the interval 4.375 to 4.5. Again, we just simply repeat the process. We've got a half multiplied by the 4.375 plus 4.5. So our x3 value we're going to use is 4.4375. So again, putting the value of x3 into our functional notation equation, we simply replace the x value with the 4.4375 and evaluate. This time we get a value of positive 0.7. So now we've got a change in the remainder. So there's a change in sign at x is equal to 4.4375. It's now positive remainder from our calculation. So we know from our previous work that the remainder for 4.375 was a negative value, but the remainder for 4.4375 is positive. Then our interval we now need to review is x is equal to 4.375 and x is equal to 4.4375. So now we're keeping the lower limit, but we're going to reduce the upper limit for the next iteration. So now for our fourth iteration, we've got the interval range of 4.375 to 4.4375. Again, we can work out the average of the x1, x2 to give us the x3, and that works out to be 4.40625. What we now notice is that from the third iteration, the x3 value was 4.4375, and from our fourth iteration, the x3 value is 4.40625. And if we're trying to find a solution to two significant figures, then we have that because in iteration 3 we've got 4.4, the two significant figures, and iteration 4 we've got 4.4, the two significant figures. So we can say now that a root occurs near to the x is equal to 4.40625 value, but at two significant figures, that is x is equal to 4.4. Please note for reference there is a numerical mistake on this slide in iteration 4 as shown here. It doesn't affect the solution as outlined on the slide. Exercise 2, we're asked to solve the equation y is equal to 3x squared minus 10x equal to 14 for a negative root this time and two three significant figures. Answers shown in the brackets here. Don't forget from example 1, rearranging the above equation and using functional notation, we're actually solving the equation function of x is equal to 3x squared minus 10x minus 14. I encourage you to stop the presentation here and solve this equation for the negative root to three significant figures. You need to define an interval for yourselves. If you go back to the table on the previous slide, you can see that a negative value of x occurs between negative 1 and negative 2. We have a change of sign on the remainder here, so that means there must be a root between x is equal to negative 1 and x equal to negative 2, so there's your starting increment. The solution is shown on the following slide. Exercise 2 solution. We're asked to solve the equation y is equal to 3x squared minus 10x equal to 14, this time finding the negative root to three significant figures. Don't forget from the previous example 1, we rearrange the equation in functional notation as function of x is equal to 3x squared minus 10x minus 14. So in part 2 of exercise 2, we're finding the negative root. Now from the table on the previous slide, a root occurs between x is equal to negative 1 and x is equal to negative 2. Here's the table, and we can see when x is equal to negative 1, we had a remainder of negative 1. When x is equal to negative 2, we have a remainder of positive 18. So a sign change occurs here, so our interval will be between x is equal to negative 1 and x is equal to negative 2 to find the negative root. So we're going to start by finding the midpoint between x is equal to negative 1 and x is equal to negative 2. So averaging negative 1, negative 2, we get a value of negative 1.5. If we put the value of negative 1.5 into the above functional equation, we get a function of x, function of negative 1.5 now, is equal to 3 multiplied by the x squared, which is negative 1.5 squared, minus 10 multiplied by negative 1.5 minus 14. That gives a remainder of 7.75, which is positive. We know from our table on the previous slide that when x is equal to negative 1, we had a negative remainder. X is equal to negative 1 and negative remainder. We just calculated above when x is equal to negative 1.5, we now have a positive remainder, therefore a root must occur between x is equal to negative 1 and x is equal to negative 1.5. If we go back to the graph on the previous slide, we can clearly see that the negative root does occur between negative 1 and negative 1.5 on the x-axis. So now all we're going to do is undertake the process we had in example 1, starting with the range of negative 1.5 to negative 1. So in this case, for our first iteration, x1 is equal to negative 1.5, the lower limit, and x2 is equal to negative 1, the upper limit. Calculating x3, which is the average of x1 plus x2, we find that the x3 is negative 1.25. We now put the value of negative 1.25 into our functional equation for the x3, so we get 3 multiplied by x squared, 3 multiplied by the negative 1.25 squared, minus 10 multiplied by the negative 1.25, and then minus 14. Gives a value of 2.25 for the remainder. So now from iteration 1, as the remainder x is equal to negative 1 is negative, from our table on the previous slide, and calculating above, when x is equal to negative 1.25, we have a positive remainder, positive positive 2.25 in this case, then a root must occur between the x is equal to negative 1.25 and x is equal to negative 1 value. So iteration number 2 starts with x1 now is negative 1.25 and x2 is negative 1. We go through exactly the same process as for iteration 1, working out the value of x3 from the average of x1 and x2 and putting the value of x3 into our equation for the function of x, and we get a remainder of 1.05. Again, that's a positive remainder, so there's no change in the sign at x is equal to negative 1.125, still positive. So a root occurs between the x is equal to negative 1.125 and x is equal to negative 1, because the remainder at negative 1.125 is positive and the remainder at negative 1 is negative. So now our interval width is going to be from negative 1.125 to negative 1. Repeat the process again. We get now an x3 of negative 1.0625. Putting that value into our functional equation, we get a remainder of positive 0.012. Still no change in sign. At x is equal to negative 1.0625, it's still positive remainder. So the root occurs between the x is equal to negative 1.0625 and again the x is equal to negative 1. Please note for reference, there is a numerical mistake on this slide in iteration 1 as shown here, but it does not affect the solution as outlined on the slide. Exercise 2 continued. So our fourth iteration is between an x1 value of negative 1.0625 and x2 of negative 1. Working out the x3, the average of the x1, x2, gives us a value of negative 1.03125. And putting the value of x3 into our functional equation, we get 3 multiplied by the negative 1.03125 squared minus 10 multiplied by the negative 1.03125 minus 14. That gives us a remainder of negative 0.497. We now have a change of sign at x is equal to negative 1.03125. It's now negative. So now a root occurs between the x is equal to negative 1.0625 with a positive remainder and the x is equal to negative 1.03125 with the negative remainder. So our fifth iteration, negative 1.0625 for the x1, negative 1.03125 for the x2. Work out the value of x3. Put the value of x3 into the equation as we did before. That gives us a remainder of negative 0.2434. So there is no change of sign here. At the x is equal to negative 1.046875. It's still negative. So therefore the root must occur between the x value of negative 1.046875, which has a negative remainder, and the x value of negative 1.0625 has a positive remainder. And the final iteration here shows the x1 is negative 1.0625 and the x2 is negative 1.046875. Working out the x3, we get negative 1.054685. Put the value of x3 into the equation. We find that the remainder now is still negative. But what we notice from the calculations is that the accuracy has been achieved for our answer. We're asked to find the solution of the negative root to 3 significant figures, and we have that because from this iteration we get negative 1.046875, so 3 significant figures, that's negative 1.05, and from the final iteration here we've got negative 1.054685, and again to 3 significant figures, that's negative 1.05. So the root occurs near the x is equal to negative 1.054685 value, but 3 significant figures, that would be x is equal to negative 1.05. So we found our solution to the accuracy required. Exercise 2 continued. We were asked to solve the equation y is equal to 3x squared minus 10x minus 14 for the negative root to 3 significant figures. The table below shows a summary of all the iterations undertaken, and the root occurs at x is equal to negative 1.05 to 3 significant figures. And from the graph on the right, that appears a reasonable estimate for the root. Example 2. We're asked to solve a cubic equation, y is equal to x cubed divided by 3 minus x squared divided by 2 minus 6x plus 5 divided by 3 equals to 0 for all positive roots. We'll state the final answer to 2 decimal places. So to solve this problem, as with all numerical solutions, we have to have some indication of where the answers reside. So using function notation, I've written the equation function of x is equal to x cubed divided by 3 minus x squared divided by 2 minus 6x plus 5 divided by 3, and I've plotted the equation below. This is the y-axis of the function of x-axis, and we can see that there are 3 roots in this particular case. 2 are positive and 1 are negative. An alternative method of finding the roots is to use trial and error. I have my function of x equation here and my remainder here. Put a value of 5 for x into the function notation equation, gave a remainder of 0.8334. Put a value of 4, gave a remainder of negative 9. So there's a sign change that occurs. So there's a root between 4 and 5 on the x-axis. Putting further values into the function of x equation, we note between x equal to 1 and x equal to 0, we get a change of sign here. So there must be a root between x is 0 and x is 1. And continue to put values in to the function of x equation, x is equals negative 3, x is negative 4, we again find a change of sign. So there must be a root between negative 3 and negative 4. And of course, those we can see from the diagram on the left-hand side. So example 2 continued. We're finding the first positive root. So from the table on the previous slide, a root occurs between x is equal to 4 and x is equal to 5. So let's try an x value of 4.5, the midpoint between 4 and 5. So for the function of x is 4.5, we get 4.5 cubed divided by 3 minus 4.5 squared divided by 2 minus 6 multiplied by 4.5 plus 5 divided by 3. That gives us a negative value for the remainder, negative 5.08. So noting now that when x equal to 4.5 we have a negative remainder. From this table when x equal to 4 we have a negative remainder, but when x equal to 5 we have a positive remainder. Then a root must occur between x is equal to 4.5 and 5. So our first iteration, x1 is 4.5 and x2 is equal to 5. Find an x3 which is the average of x1 plus x2. We then put the value of x3 into the equation above, so 4.75 cubed in this case divided by 3 minus 4.75 squared divided by 2 minus 6 multiplied by 4.75 plus 5 divided by 3 gives a negative remainder in this particular case. We know the remainder at x equal to 4.5 and x equal to 7.5 are both negative, so for iteration number 2 we use 4.75 for the lower limit and keep 5 for the upper limit. The process from there on is identical. The example 2 iterations continue on the next slide. Example 2 further iterations, and what you should find is that the x value to 2 decimal places should be 4.95. Exercise 3 requires us to solve the cubic equation shown in the previous example, so same equation here, but this time for the second positive root and also for the negative root. Answers are shown in the brackets. If we go back to the trial and error table of example 2, here we can see that the second root will occur between 0 and 1 on the x-axis, and the negative root occurs between negative 3 and negative 4. So we need to iterate between these various ranges to find the positive and the negative root. I encourage you to stop the presentation and attempt this exercise now. Work solutions are shown on the following slides. Here's exercise 3 solution. We're solving the cubic equation y is equal to x cubed divided by 3 minus x squared divided by 2 minus 6x plus 5 divided by 3 equals to 0. And this is finding the second positive root. From our trial and error process, we know that the second root occurs between x is equal to 0 and x is equal to 1. So our first try is x equal to 0.5. That gives a negative remainder. We know that when x is equal to 0, we had a positive remainder. x equals 0.5, we've just shown it's a negative remainder, so our increment we're going to start with is going to be between 0 and 0.5. So x1 is equal to 0 and x2 is equal to 0.5. I'll let you review the solution at your own pace. Exercise 3 continued. Working through the iterations, you should find to 2 decimal places the value of x is 0.27. For reference, there's a numerical error on this slide as shown here. The negative sign is missing from this final value here. It does not affect the solution as shown on the slide. Exercise 3 continued. There's a plot of the y is equal to x cubed divided by 3 minus x squared divided by 2 minus 6x plus 5 divided by 3 equation, showing the 3 roots, 2 positive roots here and here, and 1 negative. Exercise 3 continued. Again, a summary of all the iterations used to find the second positive root. The root occurs at x is equal to 0.27 to 2 decimal places. Exercise 3 continued. Again, a summary for all the solutions to find the negative root. Example 3, we're asked to use the bisection method to determine the positive root of the equation x plus 3 is equal to e to the x. Got to state the final answer to 3 decimal places. Again, as with the previous solutions, we have to find an approximate value for the initial root, the positive root. So in a solution, the first thing we need to do is rewrite the equation in function notation form. So rearranging to get all the terms onto one side of the equation, get function of x is equal to x plus 3 minus the e to the x as our equation. And as with all numerical solutions, we have to have some idea of where the root will occur, so we can do this by sketching or by trial and error. So sketching the equation, y is equal to x plus 3 minus e to the x, we find that the positive root looks around about x equals to 1.5, or by trial and error, putting values of x into the function of x equation and looking for changes of sign. Put the value of x of 3 into the function of x equation, we had a negative remainder, put the value of 2 in, negative remainder, value of 1 in, we get a positive remainder, so as a change of sign occurs between 1 and 2, so a root must occur between that range. Example 3 continues, so we're finding the positive root, and we know from the previous slide our range is going to be x is 1 to 2. So our first try is the x equal to 1.5, putting 1.5 into the function of x equation, that's 1.5 plus 3 minus e to the power of 1.5 gives a remainder of 0.018, it's a positive remainder. So we know when x is equal to 1.5 our positive remainder, and we know from the table on the previous slide when x is equal to 2 we have a negative remainder. X equal to 2, a negative remainder here. So the root must occur between x is equal to 1.5 and x is equal to 2. So our first iteration x1 is 1.5, x2 is 2 in this case, so our x3 is 1.75. We simply put the 1.75 into the function of x equation and work out the remainder. It's negative here. So as a remainder, x equal to 1.5 is positive, and x equal to 1.75 is now negative. The root occurs between the x equal to 1.5 and the x equal to 1.75. So we're going to keep the lower limit and reduce the upper limit. I'll let you follow the rest of the iterations through. Overleaf shows a full iteration table. You'll see that there are many iterations required to achieve the solution for example 3. So example 3, full listing of iterations shown here, but you should end up with a value of 1.505 to 3 decimal places for the positive root for the function of x equation. Tutorial questions for the bisection method. There are 5 questions shown here. I would strongly encourage you to attempt these questions, and the answers are shown on the left hand side here for all 5 questions. Here's the bibliography used to generate the presentation, very good reference source. The I hope this presentation has been of help to you, and thank you for viewing.